There are two players, A and B. A 30-sided die exists with faces numbered from 1 to 30. Player A chooses a number A first, then player B chooses a different number B. The die is rolled. Whoever chose the number closer to the outcome of the die wins an amount of money equal to the die roll. If the die lands exactly halfway between the two numbers, a predetermined tiebreaker can be assumed if necessary. For example, if A chooses 9, B chooses 10, and die rolls to a 7, then B pays A 7 because the number rolled is closer to A than to B. So A wins and he receives $7. So this question was asked in Jane Street quant researcher interview, and this tests a number of different concepts, uh, mainly calculating the expected values, game theory optimization, and so on. And let's see how we can solve this. So after the player picks the number, player A picks the number A, player B can choose any number B. Now, if we assume that this is our number line starting from 1 and 30 here, these are all the numbers on the die, and let's say A picks a number over here, somewhere on the number line. Now, let's say B picks a number towards the higher end, very close to 30 on this side. Now, for all values which you see here, starting from 1 up till A, these numbers would be closer to A. So for all of the die rolls wherein the outcome of the roll gives a number on this side, A would be the winner. And for all die rolls, the small portion left between B and 30 here, uh, this side, B would be the winner. Now clearly, if you see, B has a disadvantage because of him choosing a number on the higher extreme. So of course, all of the numbers in between them, we split it halfway, and half of these would be contributing to A's winning, and the other half would be to B's winning. Now, it is clear from this that B should move his number towards closer to A's in order to increase his chances of winning, because the farther his number is from A's number, you can see that the range of outcomes for which he would win becomes lower and lower. So B should pick a number adjacent to A, either A minus 1 or A plus 1. If B picks a number further away, the range of die outcomes for which B wins becomes strictly smaller, as we just saw on this number line over here. For any A, B's best options are, of course, A minus 1 and A plus 1. Now we'll calculate for both of these choices and then see what the expected values look like. So let's say B chooses A plus 1. Let's calculate the expected payoff if B picks A plus 1. If the die rolls to a value less than or equal to A, so let's say this is the number line. This is the number line. And we have A has picked this number over here. Now, this is 1 and this is 30. Now, B picks A plus 1. So this is the number picked by B, which is equal to A plus 1. Now, for all of the numbers, all of the die rolls which are less than A, this part, this would be closer to A, so A would be the winner. If the die rolls to a value greater than A, so all of these die rolls, this would be closer to B, so B would be the winner. Now, if A wins, so X is the outcome of the die roll, we assume X is the outcome, and this is distributed uniformly on 1 to 30. Now, if X is less than A, as we saw here in the number line, this part, then A would win X dollars. As stated in the question, the outcome of the die roll would be the amount the person wins. Now, B wins if X is greater than A plus 1, greater than or equal to A plus 1. That is, the payoff would be minus X dollars for A. So we are calculating these payoffs from A's perspective. So minus X dollars means A is losing the money because B is winning. So the expected payoff for A would become, so 1 by 30 is we are assuming it's uniformly distributed, the probability. And for this case, the first one, X less than or equal to A wins X dollars. So this gives us this part. over here. So starting from 1 plus 2 plus 3 till a, and each would happen with probably 1 by 30. So this is the summation. Sum k is equal to 1 to a, and from a plus 1 till 30 is x negative x dollars. So minus of a plus 1. So if I write it, the summation as minus a plus 1, a plus 2, and so on till 30 with a negative sign here, which means that a is losing this amount. So this becomes our net payoff. This is also divided by 30. So this becomes our net payoff in this case. So this is a straightforward summation. We use the formula for sum of n integers n plus 1 by 2 and calculate this expression for the case when b chooses a plus 1. Now the thing to note here is that e plus a, which is this expression, increases with a. So if you see this, if I have a on, let's say, x axis, and e a, the expected payoff for this case on y axis, increasing a would increase the payoff value. So because increasing a would increase this part of the expression a plus 1, and the other part is just a constant. So increasing a would increase this expected value. Now if b chooses a minus 1, we follow the same approach. A wins if the expected outcome, which is x, is greater than a. So let's, your number line a is here and b is just before it, a minus 1. We have 1 here, 30 here. So a wins for all of these values, all values greater than equal to a, because these are closer to a. B wins for all values less than equal to a minus 1, so all of these values. So payoff is x when x is greater than equal to a wins x dollars, and a payoff for a is minus x dollars when b wins. So we calculate the expected payoff for a, same as the previous step, 1 by 30, which is the probability, and sum from for this part, first part here, k is equal to a till 30, payoff is x dollars, and from k equals 1 till a minus 1, the payoff is minus x for a. Now we solve this expression, and this gives us the expected value. It's equal to this 1 by 30 times 465 minus a times a minus 1. Now note here again, this value, if we put a on x-axis and the expected value on y-axis, this is decreasing. The expected value is decreasing as x increases because of this part of the expression. This is just a constant. So we have calculated the expected values for both of the cases. Now comes the part of game theory. Suppose a chooses a number a. Once a commits to a, b gets to see it and chooses the best response. For example, suppose a picked 22. Now b has two options, as we saw previously. He'll choose as close to a as possible. So he'll choose either 21 just below or 23 just above. Now b wants a to do as badly as possible. B is not cooperating. If a chooses 22, b will calculate the expected value, expected payoff, as we calculated in the previous step, and b will realize that if I choose 21, a will earn $0.1, and if I choose 23, a will earn $1.37. So of course b would want a to earn as low as possible, so b would pick the option which minimizes a's earnings. So clearly b will choose 21. So after a picks 22, a's actual guaranteed payoff becomes the minimum of these two options, the minimum of expected payoff of e minus 22 and e plus 22, which is $0.1. Now a knows that b will do this. We are assuming that everyone plays rationally and chooses the best possible option, so that's something to keep in mind. This is a standard steps that you will do in problems involving game theory. So a knows b will do this. A now compares all possible a's and picks the one with the largest worst case payoff. So what a would try to do is try to maximize this expression, that is the minimum of e minus a and e plus a. Now as we just discussed, if you recall, if we have the expected payoff on y-axis, and A on x-axis, the expression for E minus was a decreasing function like this, and the expression for E plus was an increasing function like this. Now, the minimum of these two, so let's say this is a point, let's call it something P, where these intersect. Now, we are looking at the minimum of these two functions. So, which means before P, sorry, so let's say this is P. So on this side, this E plus, this is E plus, and this green one is E minus. So this is the minimum, and after crossing P, E minus is the minimum of these two. Yeah, which means this is the curve that we are looking for, which is the minimum of these two. And then on top of that, we have the maximum. So if this is our curve, the maximum of this occurs here at the corner, the point P, which we had just said, which is the intersection of E minus A and E plus A. So we'll use this point to calculate the optimal point. That the fact that the optimal would occur at E minus, and E minus A is equal to E plus A. So A chooses the point A, B sees A and chooses the response that minimizes A's payoff. Therefore, A evaluates each A by minimum, and then A picks the number A whose minimum is the largest. This is a standard minimax logic, which is used in sequential zero-sum games. So A should maximize the minimum of these two. The optimal point, as we just discussed, happens when E plus A is equal to E minus A. This expression. Now equating the above these two expressions, this gives us a value of A is equal to 21.56. The closest integer is A is equal to 22. We plug A equal to 22 in E plus A and E minus A. This gives us the expected payoff, which is $1.37 and $0.1. So B will choose 21, which gives A an expected payoff of $0.1, because B would try to minimize A's payoff. So what's the final answer? The optimal choice for A is 22. The expected return is $0.1. B chooses 21, expected return minus $0.1. So what does the strategy depend on the opponent? Yes. If B is not optimal, then A should adapt. But against a rational opponent, the equilibrium is A picks 22 and B picks 21. Would you rather be A or B? The answer is A, because with the optimal play, A has a positive expected value per game. So that's the answer to this question. I hope you like this video. Do share your comments on if any specific topic that you would want me to cover, or would you like me to cover other areas such as regression or machine learning, and I'll try to cover as many questions and topics as possible. Thanks for watching, and I'll see you in the next video.